Hello, folks. I'm creating this short lecture just to cover the bits of the hypothesis testing framework for the t-test case. It also includes example from the t-test as well as the z-test. So I'm just going to go through this uh, the hypothesis testing framework. What I'm going to do is that I'm going to start from this slide because this is kind of like two slides earlier where we left, and I'm going to walk through, and then I'm going to talk about how to compute the power of a test, and I'm going to also to help explain that I'm going to go to chapter 7 of the book, the corresponding book on statistics that we have, and I'm going to explain it from there for a more vivid and a profound explanation of the ideas. At the same time, I've also annotated some bits of the book, and I'm going to walk you through those because those are the bits that I think that are extremely important for everybody to read. So, what is the equivalent confidence level for a one-sided hypothesis test at alpha is equal to 0.05? I must remind you over here that alpha means the significance level. So this is 0.05 means 5% significance level. And I told you that significance level is also related to for instance, the confidence level. Somebody asked me this question. And I said that, if alpha is equal to 0.05, then the confidence level for a two-sided test is going to be 95%. And what is it going to be for a one-sided test? And also going to reiterate what a two-sided or a one-sided test means. So answer to this question is 90%. And why is that? So first of all, we have to understand what is a two-sided test or a one-sided test. In a two-sided test, we want to check if our test statistic is basically above or below a certain point. So, for instance, if our null hypothesis could be either so let's say if this is our null hypothesis, it touches it has a mean of 0 and it has a spread of this much, and so our alternative hypothesis could be here, which means, so for instance, if the 0 tells us that there is no significant difference between uh, post control group as well as the VR group in case of our course continuous assessment. So the null hypothesis is that the change in score is 0. There is no difference. So this is the null hypothesis, let's say. So a two-sided test checks that it could be either less than, in reality the change in difference, it could be either less, like either it could be equal to 0, in which case it satisfies the null hypothesis, or it could be either less than or greater than this value, and we have to check it. So if it could be either both greater than or less than a particular value, we do a two-sided test. We are checking on the both sides of this null hypothesis distribution. So this distribution basically relates to the null hypothesis. This can be used using a normal distribution in which we supply the mean and the standard deviation of the distribution. So this is for the null hypothesis. However, in a one hypothesis test, what we are checking is that it is either it is greater than. So either we are checking only for if it is greater than the null hypothesis, or we are checking only if it is less than the null hypothesis. We are not checking. So it cannot be the case that either it is both greater than, or either it is greater than or both less than the null hypothesis. It will be either less than that or it will be greater than that. And and somebody has asked us to check it. So for instance, a question could be that, okay, null hypothesis is that there is no difference between the test statistic, and the alternative hypothesis is that the people who are treated with VR improve their scores, depression scores, and so their depression scores are going to be negative, for instance, and they will lie over here. And then we don't check for this side of the distribution. So this is the thing. Now, when we are doing the one sided test, and if we have to check for 5% significance level, we have to take the 5% point over here. And because over here we are also going to miss this 5% point. So basically, since we are checking for the 5% point over here, so the area that is going to fall in the white region is going to be 90%. If it had been a significance level of 0.05, which is 5% significance level, for a two-sided test, then we would have taken 2.5% here and 2.5% here, right? So this is the difference. So this could be a little bit confusing, but you have to understand that, let's say in a one-sided test, we are only checking for a one-sided test. So we have to take all the significance level to here, okay? And in that case, the confidence level is going to be 90%, because it is a symmetric distribution. So we just cut a draw over here just to say that, okay, we are not going to include this region in the test as well, for the confidence level. So because the confidence level is this region plus this region minus this white region. So for a two-sided test, we have to take both sides into account. So if it is 5% level on a two-sided test, we have to, from that 5%, we have to take 2.5% over here and 2.5% over here. I hope this is clear. If somebody has a question, so they can ask me about that. So critical value. What is the appropriate T star, which is basically the corresponding value for T score, which is corresponding value in a Z test for a Z score, which is in Z scores, Z is calculated using the standard Z score tables, and T star is calculated using standard T score tables. However, it can also be calculated, T star can also be calculated using R by using this QT function. So QT, basically in this, what we supply is our the first argument is the confidence level, and the second argument is the degrees of freedom. Okay, so I'm just trying to check over here just in case what is the value of this is. And if we are using Z star, then we can compute it using Q norm. By the way, these QT and Q norm don't correspond to the Z score or T score, but basically actually they tell us the P values. They basically tell us I'm sorry to say, they basically tell us about the they tell us about the Z as well as the T scores. Okay, so I'm just going to move forward from here. So what is the appropriate T star for a confidence level for the average difference between the point prices of 0.99 and 1 carat diamond? So we did this before, and I'm just going to do this. So basically, you compute using QT, you compute T star, as well as you provide the degree of freedom. So QT is R function, which basically gives you the T score. Okay, so this is important. Okay, so I'm just going to move forward from this and try to see what are we going to do next. Okay, so so to calculate the so confidence interval, how do we calculate that? We did this exercise before, and we are going to do it again. So confidence interval is equal to point estimate plus minus margin of error, and over here this can be computed as the point estimate is that what is the difference px pt 99 minus x bar pt 1 carat gold plus minus T star for the degree of freedom multiplied by standard error. So this gives us this values. Basically, it becomes this much, and then it becomes this. This is the interval. So this is the interval which basically says that minus 15.05 to minus 2.81, this value ranges. Okay. So, and it says that we are 90% confidence that the average point price of a 0.99 carat diamond is 15.05 to 2.81, lower than the average point price of a 1 carat diamond. We did this exercise before. So there is just a recap. So if the sample sizes are not equal, we compute standard error using t-score using S1 squared over N1 plus S2 squared over N2, and we take the under root of that. So this is not N1 but N2 actually. Okay, so condition. So we have these conditions that independence within groups often verified by random variable, and if sampling without replacement, n is less than 10% of the population, and between groups, no extreme skew in the either group, and basically when the sample size is small. So you will get more clear idea when you read the book about this. So TDF is equal to point estimate minus null value divided by SE, where DF is equal to min n minus 1 n minus 2. So degree of freedom is minimum of n minus 1 n minus 2. Okay. So this is good. And confidence interval is point estimate plus minus t static degree of freedom into standard error. We know this. Okay, so this is the confidence interval. But the thing is, I have to say, confidence interval basically tells us the range in which our, our statistics values are going to lie. For instance, over here, the prices are going to be between, plus minus this interval. Okay. So now I'm going to move on to how to computing the power of a two sample test. So this is our, the kind of like the contingency table for the hypothesis test, and basically it tells us that, okay, what could be the possibilities. So if in fact our null hypothesis is true and we reject null hypothesis, right, then we have made a type 1 error, which is uh, alpha. Okay, and I'm just going to explain it in a while. So we have made the type 1 error. Type 1 error is rejecting H naught when you shouldn't have, which means that in fact H0 is true, and the probability of doing so is alpha, which is the significance level. So if your p value, and I'm going to come to that, if you compute that and that comes out to be greater than the significance level, which is, let's say, if you set it to 5% or 0.05, if it comes, the p value comes out to be greater than 0.05, then you have to actually reject the null hypothesis. But what if it is true, right? So we have to, so this p value tells us that, okay, that is the basically the probability of rejecting H0 when basically H0 is true. So if that is greater than significance level, then we have to reject H0, and if it is less than that, then we cannot reject H0. Okay, so this is a reiteration. So similarly, type 2 error is failing to reject H0 when you should have. So in the truth is that alternative hypothesis is true. In fact, the alternative hypothesis is true. However, you fail to reject H0. You couldn't reject it. So which means that you couldn't come to the conclusion that HA is true. However, in reality, it is true. So the probability of doing so is beta, and this is a little bit more complicated to calculate, but I'm going to tell you how to basically complicate this, or how to calculate this. Okay, and this value is alpha, and this value is going to be 1 minus alpha, right? And this is going to be 1 minus beta, and I'm going to show you. So what is basically the power of a test is the probability of correctly rejecting H0, and the probability of doing so is 1 minus beta. Okay, so this is what comes over here is the power of a test, that H0 is in fact false. It's not true. H0 in fact is not true, right? And we also reject it. So this is known as the power of a test. Okay, and how do we compute it? So its value is going to be 1 minus beta, and how do we compute it? I'm going to show you in a while. So this is very important because you're going to need it to do your CA, because it would be really good to reflect on the power of your test. So in hypothesis testing, we keep alpha and beta low, but there are inherent trade-offs. So, okay, we might come back to this later on. If the so type 2 error rate, if the alternative, so just remember the type 2 error is this, that it's A is 0 and we fail to reject null hypothesis. If the alternative hypothesis is actually true, what is the chance that we make a type 2 error, that we fail to reject the null hypothesis, even if we should reject it? Okay. So, in fact, the alternative hypothesis is true, and we failed to reject the null hypothesis. So we made the type 2 error. So what is the chance for that? So the answer is not obvious. If the true population average is very close to the null hypothesis value, it will be difficult to detect a difference and reject the null hypothesis. If the true population average is very different from the null hypothesis value, it will be easier for us to detect a difference. So clearly beta depends on the effect size sigma. What is the effect size? I will explain that to you in just a couple of slides as well, that what really it means to say that what an effect size is. So, okay. So, and I can maybe explain it to you using this example. So suppose a pharmaceutical company has developed a new drug for lowering blood pressure, and they are preparing a clinical trial to test the drug's effectiveness. They recruit people who are taking a particular standard blood pressure medication, and half of the subjects are given the new drug treatment, and the other half continue to take their current medication through generic looking pills to ensure blinding. Okay. What are the hypotheses for the two-sided hypothesis test in this context? So what do you think is your hypothesis, null hypothesis, and the alternative hypothesis going to be? So as the name says, null. So null means that there is no difference between the two groups, whether or not they take the treatment or not. So there is no difference, right? So the null hypothesis is going to be that mu treatment, which is the mean of the population, and mean of the population stands for mu, right? So that if even if you give them treatment or no treatment, even if they belong to the treatment group or the control group, their difference is zero. So it means that there is no difference between them. So this is the null hypothesis. That is why we can say null hypothesis. Okay. So null is associated with mostly associated with when there is no particular problem, right? So, for instance, when the innocent is not guilty, we say null hypothesis is innocent is not guilty. Alternative hypothesis is that they're guilty. And alternative hypothesis is that, so we want to do a two-sided test. So the alternative hypothesis that mu treatment minus mu control is not equal to zero, right? Otherwise, if we wanted to do a one-sided test, so we say either mu treatment is greater than mu control, or we'd say mu treatment is less than mu control, and we would check for that thing. We do it rarely, but this is what we would do in a one-sided test. But we are the question asks us to do to look for a two-sided hypothesis test to come up with the hypotheses for that. So the two-sided test says that it is not equal to zero, which means that the difference could either be less than zero or it could be greater than zero, and we have to check for both of these cases. So um, so suppose the researchers would like to run the clinical trial on patients with systolic blood pressures between 150 and 180 millimeter of mercury, mmHg. Suppose a previously published studies suggest that the standard deviation of the blood pressure will be about 12 mmHg, and the distribution of patient blood pressures will be approximately symmetric. If we had 100 patients per group, what would be the approximate standard error for difference in sampling, in sample means for the treatment and control groups? So let's say we had 100 patients per group, and the standard deviation is 12 mmHg. So what is the standard error going to be? So we compute the standard error using this. Standard error, as I showed in the previous slide, is the um, uh, divided by standard deviation over the sample size. Standard deviation of the the first sample divided by the number of samples plus standard deviation of the Sackett sample divided by the number of samples. Okay, or the sample size. Okay, and it becomes out to be 1.7. Okay, so we had this formula in one of the previous slides, and you can revisit that. So, for what values of the difference between the observed average of blood pressure in treatment and control groups? Okay, so what values of the difference between the observed averages of blood pressures in treatment and control group effect size would we reject the null hypothesis at the 5% significance level? So effect size comes here. Remember, I just talked to you about the effect size over here. Clearly, beta depends on the effect size, where beta is this probability of committing the type 2 error, right? Okay, and it says that it depends on the effect size. And now we have this effect size come into us um, to talk about. So what is the effect? What we reject the null hypothesis at 5% significance level. Okay. So effect size in this context is that to tell us that when we say that the treatment, had an effect. For instance, so what do we say that when the treatment had an effect? So for instance, if the difference in the means is, let's say, 1 mmHg, and we say, oh yeah, this is a very small difference, we don't think that the treatment had any effect, right? So we say that it has no effect. So the question is that what value of a blood pressure drop or increase would suggest us that the treatment had an effect? And then you could say, have a conversation about it, and you could say that we would at least expect it to fall by 3 mmHg, 3 points at least to have an effect. And that would be our effect size. However, let's see how it does that. Okay. Um, so, uh, So by the way, this is our null distribution, right? And we so the null distribution. What does the null distribution say? Null distribution says that there is no difference between the two groups. Okay, so then we say that okay, so this is the null distribution, and then if it is beyond this point, we reject H0, and if it is beyond this point, which means that if it is above 3 point something, then we reject H0, and if it is greater than less than minus 3 point something, then we reject 0. This value and this value are equal. By the way, what am I saying? By the way, I'm saying that if, for instance, we do, let's say, another sample, two samples, and we find that their average value or their difference comes out to be either greater than 3 mmHg or less than 3 mmHg, not 3 mm, 3 point something mmHg, or less than 3 point mmHg, then we say that we reject that. So what is this value? What is this value? So this is basically corresponds to our significance level. Okay, and I'm going to show you how to do that. So the thing is that we are trying to compute it on a 5% significance level, which means that we are going to take 2.5% region over here and 2.5% region over here, right? So remember, we are trying to compute the um, uh, effect size, which is that saying that for what values of the difference between the observed averages of blood pressure in treatment and control groups. So effect size, would we reject the null hypothesis? So clearly, uh, at the 5% confidence level, by the way. So the 5% confidence level means that our sorry, 5% significance level. I'm sorry to say that, but it is 5% significance level. 5% significance level corresponds with 95% confidence level. Okay, so the confidence level falls in this area, which is between these two bounds. So it basically covers all the 95% of the possible values that any sample could have, any reasonable sample could have. Okay, and um, what we do is that anything that falls beyond this or this is what we say has an effect, which means that if next value comes and that is either less than this value, this dotted line, it is less than this or greater than this, then we say that okay, this had an effect. This value was different than our null hypothesis. So this is what it means to say the effect size. So any new value that is below this or greater than this is said to have an effect. In other words, anything that for any new sample whose reading falls within this region, we say it has no effect. It is between this and between this. And what do these points correspond with? They correspond with 5% significant level, which means 2.5% of the region over here and 2.5% of the region over here. 2.5 plus 2.5 is equal to 5%. Okay, so this is it. How do we compute that? We take this 1.96 from the z-score table. Okay, how do we do that? And we can do it using R. By the way, we have this qnorm function, and qnorm qnorm 0.025 is equal to minus 1.959. Okay, so and similarly qnorm 0.975 is also the same value. So which means that and qnorm basically tells us what is telling us that it is telling us the z-score. Either we could have had over here t-score as well. It is up to you, but this example is using z-scores. Okay, so 1.96 into 1.7 minus 1.96 into 1.7. So it's saying that it so there is a problem with the signs over here. So the difference should be at least 3.332 or at most let's say 3.322. There is a problem with the sign over here, which means that either it should be less than minus 3.332 or it should be greater than 3.332. So any new value that has a difference, that any new, for instance, you do a new, let's say, experiment, and you take 100 samples each for the treatment and the control group, and if their difference in blood pressure reading comes out to be either less than 3.332 or greater than 3.332, then we say that the drug now has an effect, either a positive one or a negative one, right? So this is going to be negative one. It has dropped the blood pressure from this here to here, and this is the positive one. So the drug has made the blood pressure adverse. Okay, so hypertension, blood pressure, whatever you call it. So I hope this is clear. Has to be very clear. And this, by the way, I can keep on talking about it, but this will come to you very intuitively when you spare time to read it. And from the book, if you read it, it will be absolutely clear to you. And this is absolutely a very beautiful concept. My only concern is that even the book says that this can be confusing. Even the book says. And my only concern is that no matter how much I talk about it, it could still be confusing. Why? Because it is talking, and I'm just talking around points, and I'm revolving around them, kind of like moving around them, and it could be saying, oh, this is confusing. So if you read it in the book, you will be clear. Okay, I might repeat it again. It is no problem. It is up to you. So suppose that the company researchers care about finding any effect of blood pressure that is 3 mmHg or larger versus the standard medication. What is the power of the test that can detect this effect? Now we have to compute the power of the test. Now, once again, I'm going to go to this slide where the power was mentioned. So the power of the test is when you actually reject the null hypothesis, and when you reject the null hypothesis and in reality the alternative hypothesis is true. In other words, when the alternative hypothesis is in fact true and you also reject the null hypothesis, which means you kind of like accept the alternative hypothesis. Now the thing is that you could reject it, but you have to quantify it, and you quantify it using this term that is known as the power. You say, what is the power of the test net? You have to compute that. So I'm just going to talk to you about this, how to basically compute this. I'm going to have to revert to the book. Okay. So, so by the way, uh, so it does two things over here, right? So what it basically does is that it draws two distributions. One is the null distribution. The null distribution is the same as that we had on the previous slide. This is the null distribution. It has a zero mean and a standard deviation of blah blah blah, and standard error of blah blah blah. So we can kind of like, or so it is kind of like a standard normal. Oh, okay. By the way, and so this is the null distribution, which says there is no difference, and we draw this. Okay, and now the thing is that what we are trying to do now is that we are trying to compute the power. So what in power, what we do is that first of all we distribute the null distribution. Okay, and then we draw a distribution in which we say that, okay, we want to draw a distribution in which we say that uh, for the effect, for the effect size. So it says that the effect is when the blood pressure is the difference between the blood pressure for the control group and the treatment group is at least 3 mmHg. Okay, so either it is 3 mmHg or larger. So versus the standard medication. Okay, so now we are trying to do this. So what we do is that we say that, okay, we want to have at least 3 mmHg effect. So what we do is that we draw the same distribution as the null distribution over here, but it is centered at -3. So its mean, in other words, is -3. Remember that the mean of the null distribution is at 0, because it says there is no difference. So the difference is 0. Okay, there is no difference between the control and the treatment group. So it is 0. Now, since somebody said to us that, okay, the effect is -3, so we draw the same distribution over here, and this has this effect. This, I'm reiterating this. These red lines over here are the borders of the 5% significance level for the null distribution. They correspond with the null distribution. For the 3, there is this thin line going -3 over here, and this corresponds to -3.332, and this corresponds to +3.332. Okay, for the null distribution. Okay, now what we do is that we compute first of all the z-score. The z-score is, for instance, -3.332 minus -3, which is -3 is the effect size. Okay, we are computing it for this, and -3.332 is basically the the lower value of the confidence interval for the null distribution. We computed it over here. That the difference should be at least 3.332 or minus. So these should be minus 3.322 and 3 plus 3.332. Okay, so. So minus 3 is this, and we divide it by the standard error, which is 1.7. We know it. We computed it last time, and we get a z-score of minus 0.2. Okay, and for minus 0.2, what we do is that we compute the percentile using the standard z table. Okay, or using R, for instance, we can compute it. And for that, I remember I showed you in the the normal distribution lecture that we can compute it from minus 0.2. So this comes the value. So we have the p norm function. Okay, and the p norm function basically tells us 0.427, and this turned out to be what? 0.427. Okay, 0.427. P norm is basically used to compute the percentile. Okay, so we compute the percentile, and the percentile basically gives us the what do we use it as? we use it as the p-value. This corresponds with the p-value in this case. Okay. Okay, so I'm just going to move ahead. So there was something I marked over here. I just want to say, yeah. So what sample size will lead to a power of 80% for this test? So this is what we want to say is that what we want to have 80%. So what is going to be? But by the way, before I do that, I have to tell you what the power now is. So we drew the null distribution and we drew the uh, distribution for the effect, for the desired effect size. And when we plot these, so we have the straight line that corresponds with the 2.5% significance level on the left tail of the null distribution. So any area in this green curve that is below or equal to this point is basically all the area is known as the power of a test. So I'm going to explain it over here. So for instance, it is saying that what sample size will lead to a power of 80% for this test? So this is the question. I will come to how to calculate this, but I'd like to talk about the power of the as well. So it says you plot the null distribution, and then you kind of like plot the distribution for the desired effect, which is you say it has to be at least 3 mm Hg, right? So basically, you are saying that okay, it should drop the blood pressure by 3 mm Hg, which means it brings it to -3. We are not interested in a treatment that basically increases the blood pressure by 3 mm Hg. So if that had been the case, then we would have plotted this green distribution on this side, for instance, on this side of the null distribution. But we are never interested, any drug making company is not interested in seeing that, okay, we want to make a drug that is going to increase the blood pressure by 3 mmHg. They are always interested in making a drug that is going to decrease the blood pressure by a certain amount. And the question is that is it a drug that is going to decrease it by 3 mmHg? So for that, we plot this distribution. And by the way, this red line, which corresponds to the 2.5% significance level on the left side of the null distribution's tail, this point over here. So where these two distributions overlap, right? So they overlap. So any area in the green distribution that is below this point is basically known as the power of the test. Now the question is how to find the sample size. Now there are two approaches for this. Uh, one is to basically try it for different sample sizes and see what the power of the test comes out to be. And we can compute this power of the test using the uh, z-score values as well as the p-norm function, which basically tells us the percentile. So for any sample size in which we get a value of 80%, but we don't know which we get the percentile of 80%, we say that this is the power of the test. Okay, but we don't know what that sample size could be, so we have to try that. Okay, but let's see how it goes. So I'm highlighted this point, and over here it says that I made a note over here. So it says let's go back to the book. So I'm going to go back to the book, but let me try to finish what he has done over here. So standard error is equal to 3 over 2.8, 1.07142. So the question is, where did this 2.8 come from? Where did this 3 come from? This can be confusing if you look at the slides. And then he equates it to equal to this. Where did this come from? This is the problem. Okay, so n is equal to 250, blah, blah, blah. So he's done some calculations over here. So where did this come from? So to understand this, we go back to the book. So let me come back to the book. Okay. So here it is. Okay. So it is the same plot basically. Okay. If you remember, this is the one was the plot that I did previously, and this is the plot that was on the last slide that I was doing, and it says basically so this green region is the power of a test, and basically whatever it is. Now the question was that, okay, how do we compute the uh, sample size if we require a desired power of 80%? Okay, so what the sample size should be have been. So what he does is that he draws a distribution over here and this one over here. The effect size is -3, which means that the length from the middle of the green distribution, which is our desired distribution with a desired effect size, and the center of the null distribution, which has a mean of 0. So this difference from here to here is equal to 3, or let's say -3. So this difference is 3, because this is centered on -3 and this is centered on 0. So 0 minus 3 is -3, or you can say it's whatever you want to call it, +3 or -3. So this difference is 3. Now the question is that what are these two arrows? Okay. So what are these two arrows? So we have to understand this first of all. So this basically says that, okay, since we were doing, so if you remember, I just want to make it a little bit bigger. Okay. So this, if you remember that these red lines and these red lines, okay, this red line, and they correspond with the lower and the upper tails of the significance level or the confidence level of the null distribution, which is over here it is 97.5 and over here it is 2.5% percentage. Okay, and when we compute the z-score corresponding with that, so the z-score basically tells us that this length is going to be 1.96 times SE. So 1.96 is the z-score corresponding with the 95% confidence level. Similarly, this length from here to this one, it has also a length of 1.96 standard errors. So this is 1.96 standard errors away from here, and this one is 1.96 standard error over here. Okay, so now the question is, where did this 0.84 SE come here? By the way, this 0.84 SE is the distance from, by the way, from the center of the green distribution, which is about the distribution related to our effect size, to this red line, which basically corresponds with the lower tail of the null distribution. So how did that come over here? So we start by identifying that the z-score that would give us a lower tail of 80% for a moderately large sample size per group. The z-score for a lower tail of 80% would be z is equal to 0.84. Okay, so what we say is that we compute the percentile. So now the thing is, we don't know. We know a few things about this distribution, and we don't know a few things about this distribution as well. So what we know is that it is centered at -3, and to have an effect size of 80%, this point should cover 80% of the, or in other words, the area under the curve in the green distribution up till here should be 80%. Okay, it should be 80%. This is what I told you about the power of a test. Okay, that in this distribution, the area that basically comes up till this red point has to be equal to the power of the test. So because our desired power is 80%, so this area definitely is 80%. Now, which means that this corresponds with the percentile of this distribution according to the z-score table. Right now, From that percentile, what we can compute is that we can compute uh, what you call it, the z-score for this. Okay, so the z-score is, and we can look it up on the z-score table as well. Okay, so the z-score is going to come out to be equal to 0.84. Now the thing is that this this length plus this length is 0.84 into SC plus 1.96 into SC is equal to, it comes out to be, if you add 1.96 to 0.84, it comes out to be 2.8 times SE. Okay. Now, the thing is that we already know that, so this is basically the length in terms of standard errors, 2.8 times SC. Okay. 2.8 times standard error, the length from here to here and here to here. But we also know that this length is equal to 3. Okay, because the difference from, because this starts from a value of -3 and this goes to a value of 0. So this length is 3. The absolute value of this length is 3. So 2.8 SE, in other words, is the length of these two segments. The yellow one, the yellow line, and the red line. It is the sum of these two lines in terms of the standard error. So the sum of these is equal to 3. So we equate it to 3 is equal to 2.8 times SE. Okay. And then what we do is that 3 is equal to 2.8 times. We, instead of SE, we replace it with the formula of SE, which is, if you remember, S1 over S1 square over N plus S2 square over N under root, right? And what we do is that then we manipulate this equation. So what we do is that we move n over here and 3 over here. We square this equation first. So it becomes 3 squared, this becomes 2.8 squared, and this becomes, in the braces, 12 square plus 12 square divided by n. Okay, so we move n over here and 3 over here, so it becomes n is equal to 2.8 square over 3 square into 12 square plus 12 square is equal to 250.88. So this is basically so what do we get? This is what we needed. What should be the sample size for a power of 80%? So it says we need a sample size of 250.88, or in other words, let's say 251, to get a power of 80%. So 80% is that. So this is a good thing. Okay. So I'm just going to try to see if I have to go any further. So that's fine. So I've done this example and this comes out to be 251. Okay. So this is basically what tells us. So what did we learn from this? That if we, so in this exercise, what we learned was that if you want to, let's say if you want to compute a test, so because the thing is, one of the things is that it can be hard to do sampling again and again because it can be costly. It takes resources, it takes testing to be done, it takes, treatment to the control group and the treatment group and this and that, and a lot of it takes expenditures. So we can't do testing again and again and again. So what we have to do is that somebody says to us that, okay, we are, let's say, rejecting the null hypothesis. We have an effect size of 3. Let's say, in other words, we have invented a new medication for blood pressure that reduces the blood pressure of the patient by 3 mmHg, right? And we do this hypothesis testing and we see that, okay, now we can reject the null hypothesis. Somebody says, okay, can you reject the null hypothesis? And we come to conclusion that, okay, we can reject the null hypothesis. Our effect size is strong, as well as, the p-value for the null hypothesis is too low, we can reject the null hypothesis. But somebody says, okay, you can reject the null hypothesis, but what is the power of your test? So the power of the test is this, that, okay, we reject the null hypothesis, but the area that falls over here, which is basically telling us that if this medication is given to, let's say, how many people, no matter how many people, most of them are going to have this decrease in blood pressure, which is lower than this value, okay. So this basically tells us that it is going to be lower than, it is going to be lower than the significance level that we set up for the null hypothesis. It is going to be lower than this value, but how many times? It says how many times it is going to be lower than this. So then somebody says, well, we have to measure the power of the test. Power of the test is that how many percentage of the people, when they are given this treatment, they are, let's say if you give it to 1,000 people, so are there going to be 70% people, 700 people who are going to observe this decrease in blood pressure? That means that the power of the test is 70%. Are there going to be 800 people who are going to observe a decrease in the blood pressure? If the answer is yes, then 800 divided by 1,000 is equal to 80%. 80% of the people observe a decrease. So that is known as the power of the test. So somebody says, if you want to quantify it, compute the power. And then you say, how much power do you want? Somebody says 50%, somebody says 40%, somebody says, no, this is a very low value. We don't just, if it is only 50%, it means that it is just like a random test. We give a pill to two people, one person absorbs a difference and the other one doesn't absorb a difference. It is just like giving a placebo. So there is no difference. We want the power to be higher. And the power to be higher, we say how much? Somebody says, okay, 80% is good. If it decreases the blood pressure of uh, patients on average 80% of the patients to below 3 to equal to or less than 3 mmHg, then we say that our drug is successful because we set our effect size to 3 mmHg. Okay, so it says okay 80%. Now it says okay, now you say okay, but for 80% we are going to have to compute more sampling tests. We are going to have to, somebody says how much, how many samples? So this method basically tells us how to compute the sample size. So this is going to be the sample size, and we can do it using this thing, and this is what I showed you from the book. So this is it. So the recap is that we calculate required sample size for a desired level of power, calculate power for a range of sample sizes, then choose the sample size that yields that target power, usually 80% or 90%. So this is pretty much all I have to say. So there are several ways to increase power and hence decrease type 2 error rate. I must go back to that slide once again. Increase the sample size. So either you increase the sample size or decrease the standard deviation of the sample, which essentially has the same effect as increasing the sample size. It will decrease the standard error. With the smaller s, we have a better chance of distinguishing the null value from the observed point estimate. This is difficult to ensure, but cautious measurement process and limiting the population so that it is more homogeneous may help. So the idea is increase the sample size or decrease. To decrease standard deviation, once again you might as well have to increase the sample size. And how much the sample size should be increased? Somebody would say increase it by 500, somebody say increase by 1,000, and you wouldn't have the budget to do all that. So this example that we did over here basically tells us that if we need a power of a certain percent, 80%, 90%, whatever, for an 80%, this is how it is worked out. So this is the method that we use, and I showed it to you on the slides. Now I'm just going to go back to where basically I was doing this power calculation. So power is this. Power is this, that when in fact the alternative hypothesis is true. You remember, the for your medicine to be successful, or let's say your VR-based treatment of depression to be successful, your HA has to come out to be true somehow. And you can't force it to come out to be true, but you have to do the statistical testing how it goes, and you have to report the results for the CA. But to have a success in VR, whether VR is successful or not, the HA has to be true. And if HA is true, in fact, then you also have to be able to reject the null hypothesis. And this ability is known as the power of the test. So I'll conclude it with this. Okay. Thank you very much for listening to me. And I'm just going to stop sharing and then I'm going to stop recording.